Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. Let's go and get straight into the action. We are going to be taking some notes on the triangle proportionality theorem. This is also known as the side splitter theorem. So if you were here looking for the side splitter theorem, you're in the right place. In this video, we will go over the triangle proportionality theorem, or the side splitter theorem, and the converse of the triangle proportionality theorem, or the side splitter theorem. But the way that it's going to be mentioned here, guys, is it'll be within triangles, and I'll throw you the caveat that is specific to the side splitter theorem in a way that's not showing just a triangle itself later here. You'll see numerous examples, probably more than is needed, and at some point, guys, you'll just kind of see me breeze right through them super fast. All right, what is the triangle proportionality theorem? How the heck do we use it? Well, before I even talk about it, I want to make sure that you guys know that this is one of those theorems or one of those uses that it almost, you don't really need to know it fully. I'd say when you don't see a triangle drawn, you probably would, but you can solve and do these things just knowing what you know about similar triangles, what I did in my previous lectures. But this is more efficient. It's kind of like the remote exterior angle theorem, where you could work inside the triangle fully if you know what you're doing there, but this is more efficient and effective depending on what's provided for you. All right, triangle proportionality theorem, one more time, also known as the side splitter theorem. And I keep saying that because this is what I tend to call it. So if I say side splitter theorem, hopefully you know they're both the same thing. Okay, if a line is parallel to a side of a triangle, if a line, I can't even read my own thing. If a line parallel to a side of a triangle intersects the other two sides, then it divides those sides proportionally. All right, so I have this line going right here, right? It's parallel to this side right here. This line also intersected this triangle sides here and here into smaller parts A, B, C, and D. What happens is you created this proportionality unique to just those four letters in this nice fine way that you guys haven't seen yet. Let's go ahead and break down what it's going to look like by kind of building into it, if that's okay. I'm going to start with the concept, guys. We do have two triangles within here, right? We have a smaller triangle, this guy right here. I'm just going to go ahead. Sorry if it's a little disconnected there, right? But this is length A and C. And then the bigger triangle right here, notice that that length right there is not just B, of course, but it's A plus B going down the left side. And going down the right side, what do we have? Well, we have C plus D going down that, right? It's not just B, it's not just D, because those are just the split parts right there. Well, you know, we do also have, guys, similar triangles right here. Because the lines are parallel, we do have corresponding angles here congruent, and we have corresponding angles here congruent. And I don't just mean that they correspond to one another, I mean that when you have two parallel lines cut by a transversal, the name of those two are literally called corresponding angles, and we know that those are congruent. So by angle, guys, we can go ahead and deduce and state that, of course, these triangles are similar. And when triangles are similar, what happens? Corresponding sides are proportional. So the reason why I drew these two triangles, guys, was to set up a proportionality statement, and I could write here by saying the left side of the small triangle A is to the left side of the big triangle A plus B, in such a way that the right side of the triangle C is to the right side of the, bigger triangle here, C plus D. Now, this is something that you already knew. This is something you already practiced. This is how we would generally go about this problem. But there's even a faster, shorter way to do it based on what's provided for you here if you just had these parts. And let's go ahead and find out what that thing is. And the way I'm going to do it, guys, I'm going to start by doing a little cross multiplication. I'm going to multiply A with C plus D. And I'm going to multiply C with A plus B. If I distribute this, and if I rewrite these parts alphabetically, make sure that when I multiply, I'll just write everything alphabetically to, just be easier to look for. A times C is AC. A times D is AD. C times A is AC, again, alphabetical. C times B is BC. Let's subtract AC from both sides because it exists on both sides. Just, cleans things up a little bit. Boom, boom, they are gone. What are you left with there? AD equals BC. And if I were to kind of give some cleanliness regarding a proportion here, guys, what would happen if I, let's see, divided both sides by D to cancel this D here, and divided both sides by B to cancel this B here? You're left with the following statement. A over B equals C over D. This, Ladies and gentlemen, this is the triangle proportionality theorem at play, or the side splitter theorem. Let's go ahead and see what we found here. It divides those sides proportionally. This side, the left side, was divided into segments A and B in such a way that there's a ratio I can build, A over B, that's going to be equal to the other side divided into the segments C and D, and I get C over D. Yeah, this is a little bit cleaner than A over A plus B equals C over C plus D. It's just a little bit faster there. And like I said, almost one of those things. You don't have to do all this build-up stuff. The point is you can skip this part when it comes to solving and just cross multiply from here. A little bit cleaner, all depending on what's provided, and it might be a real time saver. And you know, like I said, if you don't have a triangle in view, it will also help. I'll show you what I mean by that a little bit down the line in this video. But yeah, guys, we're going to use this, and you're going to hear me say A over B equals C over D. So picture what this looks like when I say it. I'll start from the vertex. If it makes it easy for you, I'll start from the vertex and expand out. A over B equals C over D. Okay. So we're going to look at numerous examples. After a few, you're going to say, all right, let's go and move on. So let's go ahead and take a look at some of these right now. All right, find the length of each segment. We'll find the length of segment CY right here. Now, as you can tell, this is part of a segmented portion. Once this line right here, that's parallel to this third side, by the way, intersected these sides here, and that's what we're trying to find, one of the segmented portions, and we're going to use the side splitter theorem for that. See, I said side splitter theorem right there. So starting from my vertex, guys, I'll do A over B equals C over D, and in this case, D is the unknown. D is the CY. So I'll do A over B equals C over D. Straight up side splitter theorem in play. All right. Now I can cross multiply here, and you know, I use that term in a way that I trust that you know what that means when it comes to proportionality. I'm going to save time for us to do that, and eventually I'll probably next time I just won't even draw the arrows. I hope that that's okay. 9 times CY and 4 times 10, and then when I divide both sides by 9 here, then I will get CY equals 40 over 9. That does not come out to a very clean decimal, so you know, as a mixed number, guys, that would be 4 and 4/9, so that's 4.4 repeating. So I'll just go and leave it as 49, and I think I'm going to anticipate getting some fraction answers here and there. Just trust that I'm doing the math correctly, and this ratio thing comes into play. Just remember, guys, this is all about similar triangles. Because of similar triangles, we're able to make this work. You can do this with straight up triangle similarity, as you did before if you'd like, but the side splitter theorem still holds. All right, moving forward, let's do another example, and like I said, a lot of these will feel very, very samey. I hope you're okay with that. Let's find the length of PN, PN being right here. Now PN is, in this case, how about, guys, this is going to be like my A. So A over B, right? By the way, the lines are parallel. That's why we can do this. A over B equals C over D. All right, so A over B equals C over D. Now, I could say cross multiply here, but also literally, guys, all I got to do is multiply both sides by 3. Why should I multiply by 2 and bring it up here only to divide it back by 2 again? I don't have to. This already gets Pn by itself right here. So just to save time a little bit, Pn is 15 over 2. This as a decimal is a little cleaner. That is 7.5 or 7.5. I'll leave both. I'm a big improper fraction aficionado right there, but 7.5 is kind of a nice number to look at in comparison with it. It's just sometimes decimals get in the way. Yeah, that's it for the problem, guys. That's all I had to do was find Pn. Now, there can be more complex problems asked within here, I understand, and you'll probably run into those here, but I just want to make sure that you're seeing it for what it is for all the different triangles. All right, let's find DG. Same thing before. So what will this setup look like here? A over B equals C over D. 32 over 24 equals 40 over DG. DG is delta gamma. That was my sister's sorority. All right, I could cross multiply right here. In fact, I will in a second, but big numbers when we can make them smaller. 32 over 24, I can divide these by 8. I'll get 4/3. 40 over DG, clearly I can't divide anything with DG here. However, there's a 40 on the right and a 4 on the left in the numerator. If I divide both sides by 4 here, just trust me on that. 4 divided by 4 is 1. 40 divided by 4 is 10. Oh, much better for cross multiplication. So much so, I really almost have zero math to do the rest of the way. dg times 1 is dg, 3 times 10 is 30. You know what dg is? It's 30. I'm done. It's 30. We're set. And yeah, once again, the proportionality comes in play here. So this is, once again, the side splitter theorem, or triangle proportionality theorem. All right, let's do one more of one of these here. Let's find Rn here. Same setup, guys. I'm not tricking you here. So 10 over Rn, that's my A over B, the length of Rn, equals 8 over 5. Cross multiply, do, and we'll get 50 equals 8 times Rn, and divide both sides by 8. I'll get Rn equals 50 over 8. I can divide top and bottom by 2. Just to reduce the improper fraction, I'll get 25/4. There is an exact decimal. It is 6.25. Feeling good about that. All right. So we've practiced some of those there. Now, let's get some important items of note within the triangle proportionality theorem. First things first, guys. This does not apply to the parallel sides. What I mean is, although A over B equals C over D, it does not equal E over F. So look at this new E and F that I put here. Okay, it does not equal E over F. And I want you to understand why here. A is the whole left side of the small triangle. C is the whole right side of the small triangle. E is the whole bottom side of the small triangle. F may be the whole bottom side of the large triangle here. B and D are not the whole left and right sides of the bottom of the large triangle, guys. B is not the whole left side. A plus B is. See, when you do proportionality, you have to make sure that parts correspond the right way. I can say left side of small triangle to left side of whole triangle and things like that. So I could do, guys, I could say A over A plus B equals C over C plus D equals E over F, not E plus F, because E and F were never split. These sides were never split. This is whole side, whole side, whole side, whole side, whole side, whole side. So this is true, this is not. So don't be tricked by seeing these parts here, think you can apply side splitter theorem. That goes right back to triangle similarity. You have to go whole sides all within there. So that's number one. None of these other problems showed it because that wouldn't have applied the side splitter theorem. Number two, and I want to bring that up right there. Let me just erase all this in one. Let's see. Give me 1 second. There we go. Okay, number two, here, your figure may not, or may only appear as a focused part of a triangle, but the theorem still applies so long as the lines are parallel. This is where we might say side splitter theorem a little more than triangle proportionality theorem. And I want you to make sense of this, guys. We can still use A over B equals C over D right with what you're looking at right there. Because what we are kind of looking at, if you think about it, or if I visualize it for you, I could kind of make a triangle out of this thing. I'm trying to thicken it right here. Let's see. I could make a triangle out of this thing if I just, extend these lines, right? If I extend these lines here, I do have a triangle, and you're like saying, well, wait a second, A was up here. Yeah, but I mean, even if I gave this, E and F right here, E to F is to, well, here's another triangle right there, or here's one right there. This is all within that same ilk of what we're doing, right? It's all about triangle similarity that brings about the side splitter portion because of the corresponding angles and such, right? So I can still build that over time. This still applies. This is why I might say side splitter theorem more than triangle proportionality theorem, because you don't see the triangle here. But this still applies to these problems. I don't have any problems like this. I just want to make sure you know. All right, let's go ahead and jump to after we've done the triangle proportionality theorem, let's do the converse. And if you recall, guys, the triangle proportionality theorem says when lines are parallel, then the split parts are proportional. The converse flips that and says when the split parts are proportional, then those lines are parallel, or those sides are parallel here. So yes, if a line divides two sides of a triangle, it didn't say parallel. If a line divides it proportionally, then it is parallel to the third side. So if A over B equals C over D, if when you test it, it holds up, then parallel line and parallel line right there. All right. So we'll verify the lines are parallel if the proportionality is there. If not, it's not. And think about kind of what's happening there, guys. It's all about the side angle side similarity. So what you're doing is you're testing the, once again, if I kind of draw these triangles, AC, A plus B, C plus D, right? If I found out that these two parts were in proportion with one another, and once again, that goes to the whole A over B equals C over D thing. I'm not going to play the cross multiplication thing again, but if I found out this was true, this is also congruent to itself by the reflexive property. That means these two angles are congruent. What we have here is side angle side with side angle side. That would mean the triangles are similar. And when triangles are similar, that means all sets of corresponding angles are congruent, which includes literally the corresponding angles here and of course here. And you know what happens when corresponding angles are congruent, when two lines are cut by a transversal? It's the converse of the corresponding angles postulate. The lines are then parallel. So it's kind of a backwards thought to getting to the parallel lines from showing similar triangles. All we need is A over B equals C over D. Because it's the same as this, it leads us to side angle side similarity, which lets us say these angles are congruent, which means lines are parallel. A lot of stuff all built within a nutshell. All you got to do is show that A over B equals C over D, and the lines are parallel. Very cool. Same would also apply, by the way. Same would also apply for the same reason as I said before. If A over B equals C over D, then that means these lines are parallel too. Who knew? All right, so let's go ahead and take a look at, let's verify that lines MN and KL are parallel. Now, this time we're given all four sets of portions here to make this thing work. We got to test and see if 42 over 21 indeed equals, I'll put a question mark, does it equal 30 over 15? Don't play the cross multiplication game if you don't have to, guys. I'm just going to reduce these fractions. In fact, I'll divide these outright. 42 divided by 21 is 2. 30 divided by 15 is 2. 2 equals 2. You know what that means? Those are parallel. That's a check, by the way. Parallel and then check. MN and KL are indeed parallel to each other because the side splitter, the converse of the side splitter theorem, triangle proportionality theorem, holds up there. It works. I think I have two more examples here. Now this one, guys, this time, this is where you have the whole side part, and this is where, argumentatively, I think it would actually take more time to use the side splitter theorem to figure it out. Like, as in saying, hey, what's this side length here? I got to do 36 minus 20, and that's 16. And I got to do 27 minus 15, that's 12. And now let's use these things. You don't have to, because you can use it for the original ones as well, as you always knew. Before this video, your test would have been to test 20 over 36 and 15 over 27, right? Top of small triangles to top of big triangle as bottom of small triangles to bottom of big triangle. You would have tested that, and we could have said angle C is congruent to itself. So, guys, let's just use what we're given here in a way that's helpful to us. Let me not put the centimeters. That'll take a little too much. 20 over 36 equals 15 over 27. But here's the thing. You also don't want to be tricked on one of these, right? What if I didn't have, and I'll bring it back. What if I can't erase it. What if I didn't have 36 here, and here all I had was 16? You can't say 20 over 16 equals 15 over 27, right? You have to know which parts you have built. So, just be cautious, be wary. Okay, reducing the fraction is all. That's what we're looking to do. I can divide these by, I don't know, it's not 2. 2 is not the lot. 4? I can divide by 4. So I get 5/9. Here I divide by 3 over 3, and I indeed get 5/9 as well, so that checks out. Once again, guys, even though this was technically not side splitter theorem or triangle proportionality theorem because I didn't have the split part, the test in and of itself, given the way that this is a triangle, and again, reflexive property gives the congruent, given all that, the lines are still parallel. Check, this does work. All right, I think this is the last one. And again, no change, only now we have a decimal. Is TU parallel to RS? Well, this time we are kind of putting the side splitter theorem into effect. 67.5 over 54 equals 90 over 72. All right, time to bear down here. Let's see if we can reduce this. I'm going to begin by clearing out the decimal. Now, one way we could do is literally a decimal shift of these two, turn it to 675 over 540. I'm just going to multiply it by 2 because that 0.5 times 2 gives me a whole number. So 67.5 times 2 is, I don't want to get this wrong, 135, I think. And then 54 times 2 is 108. And I don't know if that helps me because I don't know what that reduces to. I know 90 over 72, I can divide those by 9. So I'm going to get 10 over 8. Oh, I can get even larger. I can divide those by 18. And I get 5/4. All right, let's hope this gets 5/4. What can I divide these by, guys? I think 27. 27, 50. Yes. If I divide these by 27 over 27, I do get 5/4. You can kind of take my word for that. 5/4 equals 5/4. Confirmed. Once again, those split sides are proportional, guys. So yes, these lines are indeed parallel to each other. All right. And we've covered both the triangle proportionality theorem and its converse, and that ought to do it for this video. All the examples kind of end up being the same. I hope the overkill wasn't too much, especially since sometimes we see decimals and different kinds of fractions, and you know, you saw this and that. All right, so that ought to do it here, guys. This is Mr. Robinson. Thank you so much for watching. Take care.